Okay, hello everyone. Thank you for attending this second lecture of the ICYS seminar series. Many of you are still joining in, so we'll just wait for 1 minute or two. So tonight we have Brad Markle and Romilly Harris-Stuart joining us. Brad will give you us a first overview on water isotopes and ice cores, and then Romilly will follow up with some results for her from her master thesis, deepening into this subject. I am not 100% Zoom literate, I must apologize, and so I am still struggling here to admit all the participants, trying to do this automatically. Okay, well, then let me welcome our first speaker for this evening, Bradley Markle. He is an assistant professor at the University of Colorado Boulder. And before that, he completed his PhD in 2017 in the University of Washington in Seattle. He has been working with ice cores and related subjects so far. He followed up with 3 postdocs. And now he, like I said, is an assistant professor in the University of Colorado Boulder. So without further ado, I'd like to give the floor to Brad. Brad, are you there?
Yeah, can you all hear me okay?
Yeah.
Yep.
Sounds good.
Great. And just to confirm, you can see my screen okay?
You can see, yeah. I'm just trying to put you here on the screen, but yeah, it's working out so far. Please go ahead.
Great. Well, it's really nice to be here and speak with you all today. And I'm also very excited to hear from our second speaker this evening. And yeah, so I'm going to give a pretty broad overview of the use of water isotope ratios in ice cores and how we can use them to understand climate in the past. It'll be pretty basic level, hopefully a little bit of review for most of you, something a little bit new for some of you, and then depending on how fast I speak, maybe a little bit of new research at the end. I can't actually see the chat or the hands or anything, so if you have a question partway through, maybe put it in the chat and Lucas can let me know. Otherwise, you can save until the end and there should be time for questions at the end. Yeah, it's great to be here and talk with you all today. So as I said, we're going to start really broad, and that means we're just going to talk about what an isotope is. So water, of course, is made out of oxygen and hydrogen. And if you go and look at the oxygen, for example, in all the water in the world, most of it will be oxygen 16, meaning it has 8 protons and 8 neutrons in the nucleus. Rarely, some of the oxygens in that water will be oxygen 18, which means it has a couple extra neutrons in there. And despite that, those heavier isotopes are pretty rare, and the mass difference is very small, it's just a couple of neutrons, we can actually measure the relative amount of the heavy oxygen 18 isotope to the lighter oxygen 16 isotope in any sample of water or ice or anything that we find. We often report that ratio of the heavy to light isotope as a delta value. That is, it's just this ratio, but normalized with respect to that same ratio in average ocean water. So if the delta 18O of a sample of water that you measure is a negative value, that means it has much less of the heavier isotope than average ocean water. Water, of course, also has hydrogen in it. Hydrogen also has stable isotopes like deuterium. We can measure the relative amount of deuterium and normal hydrogen and report that in a delta deuterium value as well. Hopefully this is very much review for everyone. So the only reason I'm interested in this is because as water moves through the Earth's hydrological system, these ratios, these delta values of the different stable isotopes change, and they change with respect to the climatological conditions that that water experiences. So because of that, we can go somewhere where snow falls and measure the water isotopes in the snow that accumulated there, say in Antarctica, over hundreds or thousands or hundreds of thousands of years, right? So this is the delta 18O of layers of ice in an ice core from West Antarctica. And on the left side is the delta 18O today, and on the right side is the delta 18O 70,000 years ago. So water isotopes, this is just a measure of the chemistry of the water in the ice, but we can use it as a proxy to understand how the climate changed in the past. So the first main point I want to make today is that all interpretation of water isotope ratios in terms of climate in the past, that is their use as a proxy, requires a model. And we often think about a disconnect between the field of geochemistry and modeling, but all interpretation of water isotopes requires a model. However, models come in many forms, right? So you can have qualitative models or quantitative models. You can have empirical or statistical models, or you can have sort of physics-based numerical models. Models can be very simple or they can be extremely complex. But it always takes a model to make interpretations. And models are just tools for asking questions. And so sometimes the right model to use really depends on your question. It isn't always the case that the most advanced, most complex model is the right tool for your question. So we're going to start by just talking about a couple of the simplest models to use for understanding water isotopes in the past. And the first one is one I'm sure everyone is pretty familiar with. This is just an empirical observation-based model. You can go measure the water isotope ratios like the delta 18O of precipitation from all over the world. I'm showing it against latitude on the left, or you can plot it against the surface temperature of the locations where you took those samples. I'm showing that on the right. And you can see that there is some quite actually clear relationship between the surface temperature somewhere and the delta 18O of the precipitation that's falling there. So even without understanding the underlying physics, we could make from this just a statistical model to help us use water isotope ratios of precipitation that we measure either now or in the past to understand the temperature there. Of course, it's always useful to understand the physics underlying the system you're interested in. So we're next going to talk about a very simple but physically based conceptual model of why water isotope ratios are related to the temperature of where the precipitation is falling. If there are any questions, by the way, put them in the chat and maybe Lucas can let me know. Okay, so now we're going to talk about a simple conceptual model. This is, again, one many of you are probably pretty familiar with. The main idea here is that water evaporates from the oceans at low latitudes. And then because of the basic functioning of the climate system, water is transported to the poles. And the main thing that our water that has evaporated out of the ocean and is transported to the poles is going to experience on that journey is a very steep temperature gradient. It's pretty warm at the low latitudes where it's evaporating. It's very cold, for example, over Antarctica. So it turns out that the amount of water vapor that the air can hold is dependent on temperature. In fact, it's non-linearly dependent on temperature. This is the Clausius-Clapeyron relationship. What I'm showing here is the saturated mixing ratio of air given this temperature gradient. So as our cloud of water is being transported towards the pole, it's going to encounter colder temperatures. That's going to mean that that air can no longer hold as much water as it started with. And some of that water is going to be forced to condense and precipitate. Now, every time water changes phase, it can fractionate. Indeed, what happens is the heavier isotopes preferentially want to be in the lower energy state. So in this case, going from vapor to, say, liquid precipitation, the heavier isotopes are going to prefer to be in the liquid. And so as our air parcel is taking its journey, it's going to progressively lose heavier isotopes to the precipitation that is forced to fall out of it. And so along this path, the delta value of the vapor and the delta value of the precipitation falling out of it is going to get increasingly more negative. That is depleted in the heavier isotopes as they're progressively lost along the way. So this now gets us almost to why we can use this as a temperature proxy. So we can imagine now, if we held everything the same, but cooled down our little favorite location in Antarctica, for example, that air parcel would be forced to cool a little bit more to get to the same place, which means it would condense a little bit more to get to the same place, which means it would force the water in it to fractionate a little bit more to get to the same place, and the delta value of the precipitation falling there would go down. Likewise, if we warmed the temperature up a little bit, it wouldn't have to condense out as much, wouldn't fractionate as much, and the delta value would go up. So this is the basic underlying reason why water isotopes of particularly high latitude precipitation are really sensitive to temperature. And it's linked to two fundamentally nonlinear processes. One is Rayleigh distillation, this progressive loss of heavy isotopes. And the other is the Clausius-Clapeyron relationship. And because of that, it makes it a very strong lever on the delta 18O or delta deuterium of water falling out as precipitation. Yeah, and by the way, it's a strong lever, it's a strong process. It's also not incidental to the climate system, but actually fundamental to how the climate system works. The Earth's surface absorbs energy from the sun. It transfers that energy to the atmosphere. A big component of that energy that transfers to the atmosphere is the latent heat associated with evaporating moisture. And then that climate system transports that energy from the equator to the poles, from where it's gaining too much energy to where it's losing energy to space. So this overall process of the hydrological cycle is intimately connected with how the climate system actually works. Okay, but this is not the only thing that's going on, not even close. So let me remind myself. Yeah, so one complication to this like very simple picture is that it's not just the temperature at the final precipitation place that matters, right? That is, it's not just temperature change at that final precipitation place that matters. You can also just see, even from this simple conceptual model, that temperature at where the water is evaporating from must also matter, because it is setting this total gradient through which the water is distilled. It matters for a bunch of other reasons too, but that's one of them. So because of this, if we're trying to understand temperature change in the past, from measurements of water isotope ratios in ice cores, for example, we really actually want to understand at least two different temperatures. One, the temperature at, like, for example, the ice core site where we drilled this ice core, how the temperature changed there, but also the temperature at where that water initially evaporated from. Now, so that's two unknowns we have. So we're going to need two constraints to start even attempting to reconstruct those things. And luckily, water has two sets of stable isotopes, right? So we have both the delta 18O and the delta deuterium. It turns out that either delta 18O or delta deuterium are really sensitive to this temperature at the condensation site over our ice core site, and a little bit sensitive to the evaporation temperature. But a second order parameter, the deuterium excess, that's the weighted difference between the delta 18O and the delta deuterium, is more sensitive to the evaporation source temperatures. Now, full honesty here, it's not only sensitive to that, it's actually sensitive to a bunch of other things, but it is influenced by that initial evaporation temperature quite strongly. So we fortunately now have two unique bits of information: the weighted difference between the delta 18O and the delta deuterium, what's called the deuterium excess, and then also our original delta 18O. So with those two things, we can start to maybe reconstruct both of these different temperature histories, the history of temperature at the evaporation source and at where that water is condensing. Okay, so that's one complication. There's a bunch of others. Water that precipitates over the ice sheet doesn't evaporate from a single place. In fact, it evaporates from a huge swath of the oceans, right? So in the upper right panel, there's a graph of histograms, and they're histograms with respect to latitude. And they are the evaporation source for a bunch of different Antarctic ice core sites. And so you can see that that water that eventually falls as precipitation in Antarctica is actually coming from a huge swath of the southern hemisphere. So it's not just one pathway we need to consider. Likewise, the water that falls as snow on Antarctica isn't condensing at one temperature necessarily, but it could be possibly condensing all throughout the atmospheric column, which of course has a huge range of temperatures and temperatures that vary over different time scales. And so there's a relationship between the temperature of condensation, what the water isotopes feel, and the actual surface temperature that we can measure. So on the lower panel, you can see an estimate of that relationship from a model. These are just a couple of the complications. Turns out there's a whole bunch of other ones. There's many different processes driving water isotope fractionation during transport that I didn't really talk about. And then even after the water falls as snow over the ice sheet, it can sit there and potentially interact with the snow around it, especially as it gets buried deeper in the ice sheet. And also the atmosphere overlaying that snow. So it can sit there and it potentially interact. And so there's a bunch of like new cutting edge research that's trying to better understand those processes. It's all really quite new and quite exciting. And I'm pretty sure we'll get to hear a little bit about some of that from Romilly here in a little bit. So these are a bunch of complications that make this simple process not the full story. But the simple process still is happening regardless. So let's see, what am I talking about next here? Yeah, so now we're gonna move to a relatively simple numerical model. And we're gonna try to take into account some of these complications. For example, the fact that water comes from a huge range of different evaporation sources to reach one single ice core site. But we're gonna ignore some of the others. In particular, we're not gonna consider the complications associated with what could happen to the water isotope ratios of the snow after it falls. But those might be important. So what we're gonna do is we're gonna write down our best guess at the geochemical and physical equations that govern the transport and fractionation of water from a whole bunch of different sources and potential condensation temperatures. And you can see some examples here on the right. The colors here are different evaporation source temperatures, and then the thermodynamic pathways, both in pressure, the saturated mixing ratio of those pathways, and then the ultimate delta 18O of those pathways as a function of the condensation temperature derived from this simple numerical model. And what we're going to do next is we're going to take this model and we're going to run it through a huge possible climate space. So the way to think about this is we're going to take our initial temperature gradient and we're going to warm up the initial evaporation temperature a little bit and run the model again. And then we're going to cool down the condensation site final temperature a little bit, and we're going to run the model again. We're going to vary this over and over again, creating a whole possible space of different temperature gradients through which water can be distilled. And the result of that is going to be a bunch of maps. And so on the left, if you look at the left figure, the upper left panel, this is a map of delta 18O, of precipitation, arising from a whole bunch of different temperature pathways defined by the evaporation temperature on the y-axis and the condensation temperature on the x-axis. And the panel to the right is the deuterium for those same set of pathways. And then the panel on the lower left is the deuterium excess for the same set of pathways. And we can ignore the other panel for now. So what this is a whole field of possible water isotope ratios that result from possible climates, that is, possible different temperature gradients. Then what we're going to do is we're going to invert these maps so that we now have, instead of two different temperatures on the x and y axis, we have delta 18O and deuterium excess on the x and y axis. And the surfaces now are the final temperature of condensation and the final temperature of evaporation. The reason we're going to do this is now we can use that map, or those two maps on the right, to reconstruct these two temperatures from measurements of delta 18O and deuterium excess in samples from an ice core, right? So we just take a bit of ice, we measure the delta 18O, say it's -30. We can go to our graph on the upper right, look up where -30 is, then we can measure the deuterium excess on the y-axis and just look up what the model thinks the condensation temperature is for that unique combination of O18 and deuterium excess. Does that make sense? Maybe? All right. So then we can take the O18 and deuterium excess records from a bunch of different ice cores all over Antarctica and use the results of this model to reconstruct both the temperature of condensation and the temperature of evaporation that the model thinks could lead to those unique values of O18 and deuterium excess. So if we do that, this is what we get. So the upper left is just a map of Antarctica, showing where all these ice cores are from. The map on the right is the evaporation temperature. So the weighted sum of these distribution of possible evaporation temperatures that lead to water getting to Antarctica. And the change in that mean evaporation temperature over the last 140,000 years for these different ice core sites. In the bottom left is the condensation temperature over Antarctica from the same reconstruction technique for all these different ice core sites. And then on the bottom right is the surface temperature, which we estimate by knowing the condensation temperature and the relationship in the climate between the mean condensation temperature and the surface temperature over Antarctica. So now we have histories of absolute temperature over tens of thousands of years. So now we can actually start to ask interesting questions about the climate. And so I only have, I think, a few minutes left. So I'll get to just a couple of the interesting questions we can start to do with this, these types of temperature reconstructions. So I guess I should mention one last thing. The value of doing this in a model, a numerical model, and in particular, a fairly simple one, is that you can change assumptions or parameters that you built into the model to see how robust your results are. So what you're seeing here on the right is the results of me changing the assumptions and parameters I put into the model many, many times, and then redoing the reconstructions of temperature to see how much they change if, for example, I don't know the fractionation factor of O18 over ice very well. And so you can start to estimate quantitatively the uncertainty associated with your temperature reconstructions. Okay, so here is a simple look at a couple of interesting things. On the upper left, we took the evaporation temperature from all these different ice core sites. They're in light blue, and then we just averaged them very naively. That's in dark blue. In the lower left, we did the same thing for the surface temperature, reconstructed from these water isotope records for all these different sites, and then just naively average them all for all the different sites in Antarctica. And not shown here, I did the same thing for the condensation temperatures. And what you can see on the right is that the evaporation temperatures, the surface temperatures, and the condensation temperatures all have similar variability, but much different magnitudes, right? The average site surface temperature in red between the last glacial period and the modern is almost 3 times more variable than the average evaporation temperatures reconstructed from those same ice cores. What's that saying? Well, the evaporation is coming from somewhere lower in latitude than the condensation place. This is saying that the higher latitude temperatures are changing more than the lower latitudes. This is polar amplification, right? We can see this in another way. I've taken the change in surface temperature for the different ice core sites. And those are the colored dots on the far left side of the left panel. This is the amount of change since the last glacial maximum reconstructed from all these sites. The colored dots in the middle of that panel are the evaporation, the change in evaporation source temperature from all these sites, plotted at the latitude of the current evaporation source, the mean of the current evaporation source as estimated from the model. And in the black circles, you can see the reconstructed sea surface temperature change since the last glacial maximum from a bunch of different marine sediment core records. So first thing you can see, the ice core record of sea surface temperatures over the Southern Ocean and the changes in them are pretty consistent with what you get from the marine sediment core records. And all of them are like a factor of 2 or 3 smaller than the temperature changes we see over Antarctica between the last glacial maximum and today. You can see this on a map on the right. You have a much more temperature change over at the Antarctic. We can compare this to what global climate models think happened between the last glacial maximum and today. And you can see, that's what I'm showing now on the right. you can see the patterns are largely similar, but there are real differences, both in the magnitude and the spatial variability in those temperature changes. So I think I'm basically out of time here. This is just the start of the types of climate dynamics questions you can start to answer when you have reconstructions of temperature, which you can get in impressive detail from water isotopes. I think I will put up some conclusions and skip like 10 slides, and happy to take any questions now.
Absolutely. Thank you so much, Brad. That was pretty comprehensive for, a short talk, but I really think you covered a lot of ground, and that was quite interesting. All right. Without further ado, I'd like to open floor for questions. So either raise a hand or write something directly in the chat, and I will, please. I will either unmute you, or I think you can request that yourself. Let's see if we have something here. In the meantime, I can squeeze myself one question. I know that you kind of avoided talking about the the logarithmic description of the deuterium excess. I read about that briefly in some paper. Is it just because empirically it matches better, would we expect, or is there some fundamental reason why it's better to use it that way?
Yeah, so this is a good question. So what Lucas is asking about is the deuterium excess parameter. That's the second order weighted difference between the delta deuterium and the delta 18O. It has historically been defined, the weighted difference is just the deviation from an expected line with a single slope between the delta 18O and the delta deuterium. And that has a slope of 8. And that's because you can just like go and look at delta 18O and delta deuterium measurements from around the world, and they have about a slope of 8. Okay. Now, the underlying physics there, you shouldn't expect a single linear slope between these things. They are fundamentally non-linear logarithmic processes. And so you can then define a slightly non-linear slope between them. And that there isn't really a good first principles slope for this. It's best to just do it empirically, and that's what folks have done.
It is purely empirical, okay.
But it makes a huge difference. So this is the linear deuterium excess from a bunch of different ice cores over the last 60,000 years on the left. This is the logarithmic deuterium excess between them. And the reason the logarithmic one are so much more coherent is because the linear one has built into it some nonlinear biases, because the underlying relationships are inherently nonlinear. I could talk a lot more about that if anyone.
No, but that clears it up. Okay, let's see here in the chat. Aha, okay, sorry. We have a question from Alexis. Except temperature, which you well presented, which parameters are water isotopes correlated to?
Yeah, that's a great question. So honestly, temperature is a big one, but many things that can affect the thermodynamic pathway that water experiences can change the water isotope ratios. Basically, anything that you can do to cause water to change phase will influence the fractionation. In particular, during the initial evaporation out of the ocean, the relative humidity of the overlying air is extremely important. Turns out over really long time periods, relative humidity probably doesn't change a whole lot, but it certainly can over short time periods. And it does so in ways that might not be super well correlated with the surface temperature changes there. So if we had a third water isotope parameter, O17 excess, for example, we could maybe think about reconstructing 3 different variables, like the temperature at the source, the temperature at the condensation site, and the relative humidity at the source. There's a bunch of other parameters that can really drive it as well, especially at short time scales. But yeah, those are probably the biggest ones at long time scales. With the caveat that there's some other things that can change the variations in the water isotopes as they sit in the snow in Antarctica for long periods of time. They can start to diffuse within the firn, for example. And that can be dependent both on temperature and accumulation rates, for example.
All right, perhaps we have time for one last question, because this is getting interesting. You have here a question from Christo Buizer that says, how realistic is the assumption that the boundary layer inversion was the same in the last glacial maximum?
Oh yeah, this is a great question. Thanks, Christo. So the reason this is an important question is water isotopes feel the temperature of condensation. But often what we really care about is the temperature at the surface of the Earth. And that's related by some relationship. And as what Christo is pointing out here is that there's strong inversions in Antarctica, such that the condensation temperature, and in general, the temperature above the surface is often warmer than the surface itself. So part of Christo's question here is if you look at that relationship in the modern, and then use that to interpret temperature variability in the past, how smart is that? Like maybe that relationship changed. And it certainly could. But I think one good point in the favor of being able to use the modern relationship is that this is something that's mostly dependent on the temperature itself. And we can sample a huge range of temperature in the modern climate, right? Like the difference between the difference in the surface temperature between the edge of Antarctica and the top of Antarctica is much, much bigger than the change in temperature between the last glacial maximum and now than at a single place in Antarctica. And so because a lot of the processes underlying here are dependent on temperature, and we already sample a huge range of temperature, we're getting a lot of the potential variability in this relationship. Of course, it is possible that this thing could change for other reasons, not directly related to temperature, in which case it might be bad.
All right. Well, let's not eat up too much time from our next speaker. Thank you so much, Brad, again, for this wonderful talk. I will now pass on host powers, let's say, to my colleague Delia, who will take over from now. Okay.